Hey YouTube, so this is problem number 58 from chapter 4 from the section on mesh versus nodes. So the problem states the variable DC current source in the circuit in figure 458 is adjusted so that the power developed by the 4 amp current source is 0. So that power developed is 0. So now we want to find IDC. And so we need to first decide which is the better method. Honestly, I first started out using the mesh method because I know this current, and they gave me this current, so I knew I would go, there would be an IA here, an IB here, and then an IC here. However, remember that the mesh method utilizes voltage drop, so when we do this mesh here, we're going to introduce a fourth variable, which is VDC. And I came up, what happened was I spent too much time on it, and I decided I kept coming up with 4 variables and 3 unknowns, and then I decided to scrap that and try the node method, and the node method ended up being much easier. Even though it didn't look like it would be, it did end up being easier. So let's go ahead and choose a node voltage method. So remember, we have a node here, a node here, a node here, and a node here. Which one is the ground? So naturally, you can use anything for the ground, but if you chose this node and this node to be the ground, remember the node voltage method uses KCL. You're going to be at a huge disadvantage because there's 3 branches connected here, and there's 3 branches connected here, so that means you're going to sum 4 currents from here and 4 currents from here. So as a rule, you always want to choose the node that has the most circuit elements. So that's going to be either this node, which has 4 circuit elements, or this node, which has 4 circuit elements. So then we need to decide, is that going to be this node or this node that is the ground? I tend to pick, so this arrow here of the current source gives us information. This tells me that the direction of the voltage rise is in that direction. So then I'm going to choose that to be my ground. Okay? So then there's going to be 3 node voltages here. So at this node there's some VA, and at this node there's some VB, and then here there's some VC, and then we'll start writing our nodal equations. So node voltage at VA, so let's go ahead and write that. So remember, so we got VA, this voltage. We're summing currents, and remember currents is voltage over resistance, so it's going to be this voltage minus the sum of these voltages, right? So this current is what we're writing, so that's going to be VA minus, okay, so what are we minusing? We're minusing this voltage and we're minusing that voltage, so minus VB for sure. But what's this? Is it a plus or is it a minus? Well, when the current goes through here, it's going from positive to minus, so it's going through a voltage drop. So obviously when you go from plus to minus, you're going down. So that tells me that this is really minus 240. So that's my net voltage, and then that's over a resistance of 12. So that's the first current. Now this current is much more straightforward. That current is VA minus VB, and that's over 20. Now this current here is VA over 15, because that's this node here is our ground node. So plus VA over 15, and finally this current here leaving the node is going to be negative 4. Because it's negative 4 because the direction of the current is going into the node, which means that's a minus. All that is equal to 0. So node voltage at VB. So it's going to be the sum of this voltage, right? So this current right here, we know it's going to be VB for sure. But what's this sign? So again, this voltage, this current leaving here is going to go through a voltage, it's going to go through a minus to a plus, so it's going through a voltage rise. So the sign is going to be plus 240, and that's going to be minus VA over 12. That's the first current. The next current is VB minus VA over 20. And then lastly, this current here is going to be VB minus VC over 40. And that's equal to 0. And then now, node voltage at VC is going to be VC minus VB. That's over 40. Next current is VC over 50. And then this current is going to be this IDC coming into VC. So that's going to be minus IDC. That's equal to 0. So then when I did this method, I was like, oh crap. I have the same problem. I have VA, VB, VC, and IDC, and I have four equations, 3 equations and 4 unknowns. But if you think about it, the information that the problem gives you is that as a problem requirement, we're changing this variable current source such that this is voltage, or this power is 0. Remember, power is voltage times resistance, or voltage times current. So we know the current is 4, so therefore for this to be 0, or power to be 0, it must mean that the voltage is 0. So that means this voltage is 0, meaning VA is equal to 0. So now I have 3 equations and 3 unknowns. Yes, now, because of the criteria that the power is 0, then VA becomes 0, so that's 0. So now I'm down to, this term goes away altogether because that's 0, 0, 0. Okay, so now we have 3 equations and 3 unknowns, and we can construct a matrix and have everything solved that way. So our 3 unknowns are going to be VB, VC, IDC, and then constants. Okay, make sure everybody can see everything. Looks good. Okay, so let's go ahead and inventory the coefficients. So the first term is negative VB over 12, so that's going to be negative 1/12 for the VB. The next term is negative 240 over 12, which is 20, I'm pretty sure, but I'm unbelievably horrible at basic arithmetic. So negative 20 will go on the other side as positive 20. So yes, I'm that horrible that I have to just double check because it causes me a lot of grief when I make really basic mistakes. So then on this side I have a positive 20. Next term is, well, the VA is 0, so negative VB. Again, we have a VB term of negative 1 over 20, so minus 1/20. And then a negative 4, so it's going to come on this side as a positive 4 and combine with this to be 24. So we got 0 VC and 0 for IDC. And at this point we could solve for a VB, but why do that when we have a fancy calculator? So at VB we have 1/12. And then we have positive 20, which is going to come on the other side as negative 20. And then we have a 120 plus 120 for VB. And then we have another VB term of 140. And then last term is negative 140 for VC. And then 0 IDCs. And then for the third equation, we have, and let's just, okay, so for the third equation, we have 140 for VC. And then we have negative 140 for VB. And then for VC, we have 150. And then IDC, we have negative 1. So, and then 0. Okay, so let's enter this information into our calculator and find out what everything is. Okay, so we have 3 equations and 3 unknowns, so we've got negative 1 divided by 20 plus, minus 1 divided by 20. So 0, oopsies. Oh man. Okay, so negative 1 divided by 12 minus 1 divided by 20. 0, 0, 24. So 1/12 plus 120 plus 140 and then negative 1 over 40, 0, negative 20. Then negative 1 divided by 40, and then 1 divided by 40 plus 1 divided by 50, negative 1 and 0. Solve. Okay, so this jams up. So the answer to this problem then is going to be, so when you solve that matrix, you just find that VB is negative 180 volts, and VC is negative 340 volts, and IDC is negative 10.8 amps, and that's what we were looking for, and that's the answer to the problem. And by the way, this problem is entirely solvable by mesh. I just didn't really have time to do it, but I suspect the fourth equation would come from here, just using V is equal to IR, but unfortunately, I don't have a heck of a lot of time as a single parent working a full-time job to really do everything. So today I just took the path of least resistance. If the node method hadn't panned out for me the way it did, then I probably would have forced myself to solve it with mesh. But I encourage someone out there in the YouTube community to find that fourth equation, solve it, and post a response video. That would be really cool. Okay, you guys, good luck on your exams.